Good afternoon, everybody. I'm Polina Nikeva. I'm a faculty member in Material Science and Engineering Department, and I'm also serve as a department head. And it is my great pleasure to welcome you all to our Wulff lecture, probably and actually most definitely the most important lecture that our department offers throughout the year. And Wulff lectures have been instituted in memory of John Wulff, who was a creator of 3091, Introduction to Solid-State Chemistry, which is by far the most important class you're going to take at MIT if you're a student. And all freshmen should, or other year students also should. And John Wulff was a provocative and talented teacher, and this lecture is really intended to commemorate his accomplishments in education of material scientists and engineers and inspire young students and to major in material science and engineering and to really understand what our field really is. And today we are extremely fortunate to have Dr. Diran Apelian joining us as our Wulff lecturer, who is really represents both the spirit of material science and engineering and spirit of enthusiasm as really incarnated in the sort of in John Wulff style. Dr. Apelian is an alum of this institute. He got his doctoral degree in our department. Since after that, he proceeded to have a celebrated career in metallurgy, first in industry and then at Drexel University, where he served as a dean and a provost. He then moved to Worcester Polytechnic Institute and served as a provost there. And after few years, he decided, well, few years was about 28 years, he decided that the weather was better in California, and now he works, he is on the faculty at the University of California, Irvine, and leads their strategy. And Dr. Apelian has written many, many important articles in the field of solidification, metallurgy, materials processing, and I think more than 700 articles. He also authored many patents. He's a member of National Academy of Engineering, National Academy of Inventors. He's a member of National European Academy of Engineering. And he's really probably one of the most celebrated metallurgists of our time. So I'm just so beyond grateful that he is our Wulff lecturer today. So please help me welcome Dr. Apelian.
Well, Paulina, thank you so much. I've been introduced before, but not so elegantly and gracefully. Thank you for that. I'm so happy to be here, and thank you for coming. And I will try to tell you a little bit about the topic that you see on the slide there. But I'm going to do that by first talking about John Wulff, that Paulina briefly mentioned about him. I was here when he was here. He retired in 72, and I was here as a graduate student between 68 and 72. So I actually remember him. The reason I wanted to put those two visuals on the slide is to show you how life changes. Because in 1952, the book that he wrote, you can see it on the slide, was about engineers and metallurgy for engineers, casting, welding, working. 20 years later, he's the pivotal figure that really gets material science and engineering foundations. The books that you see there, those 4 books, are seminal books in material science and engineering. So for the undergraduates particularly, and the graduate students who are here in the room, what you're doing now is not going to stay the same. It's going to evolve, and you better be in the driver's seat making sure that you do it. He is actually an exemplar of a person in the field who really was transformative when you think about it. In addition to all that, he was an amazing orator, an amazing, inspiring teacher. So I cannot tell you how honored I am to be giving this lecture, the Wulff Lecture, here today. My time here at MIT was also, for me personally, very transformative, and for the students who are here, the years that you spend time here are, I'm sure, years from now, you're going to look back and hopefully think about it the same way as I do. My advisor was Mert Flemings, still is an advisor, a mentor. But it's not only silvification science, but the engineering part. We really learned both of those domains. But one of the things that happened in that lab was that we were doing a lot of things with artists. The lost form process, and I, without knowing it, it wasn't by design, I got exposed to all that and found out that, it spoke to me, and I found a lot of joy in it. And to this day, aesthetics and art and cultural activities, the nexus of engineering and science really took its birth here. And at the same time, courses with Cyril Stanley Smith about the history of technology. So the education here at MIT was so holistic and has been so important in my life. On the far right is David Spencer, who was my roommate, my office mate. We both came from Pennsylvania to MIT at the same time. We graduated together. He's a co-founder of Waste to Energy, owner of Waste to Energy Corporation. So I wanted to just, there are many more photos of people I could put in there, but I wanted to mention that especially for the students here, because these years that I spent here have been so formative for me. To get on with the lecture, what I thought I'd do is to first establish some context as to why this topic is so important now, but will be even more important in the next 20, 30 years. So it's going to be really, really important in your careers. And then I want to talk about material circularity, because when we talk about recycling, it's really not about just recycling, it's about recovery, reuse of the materials that we use. So I want to talk about material circularity and I could spend a lot of time on pathways to sustainability, but obviously we don't have enough time. I'm going to give you just a few examples about that, and then try to finish up with the three axes and some closing comments. How many of you here are not in material science and engineering? Well, I'm going to try to convert you. If you look back the last 70 years, that's just a real snapshot. We don't have time to really go through every one of those examples, but it's amazing. Right? It wasn't that many years ago, MRI, CT scan, all that. Today it's like, you go to the hospital, they get it done. Contact lenses, all these things. Material science has been an amazing enabler of all of our societal things that we appreciate, enjoy, has made our quality of life so much better. The world in which we live in, a beautiful world of ours, the population, however, if you look at the numbers, and we don't have time to really delve too much into it, but just a few numbers, we've had an amazing growth of population. Entered the 20th century with, 1.6 billion people? I can remember just the reverse. And 100 years later, it's 6.1 billion. 1.6 to 6.1. All of us, of course, we drink water, we eat, we consume. So the sustainable growth, sustainability, the development of the planet Earth is a challenge, a real challenge. Now, if you look at history, or people who are historians will look at this period between 1990 and 2020 as a very pivotal moment in our civilization where the quality of life increased so much in so many people. These slides are going to be available. I don't know who I'm going to give it to, but there's a YouTube video by Hans Rosling there, about 4-minute YouTube video about the history of the world in 200 years. So, but this actually it's a profound change, but it requires material issues and challenges that are also an opportunity. So if you think about Maslow's hierarchy of needs in psychology, if you think about a similar kind of metaphorical need of our society and the challenges, we need energy, we need food, we need water, mobility, shelter, health, right? Basic needs. All of these things are enabled by material science and engineering. Take any one of those pillars, material science and engineering has been the pivotal, quintessential technological innovations that enable them to happen. Now, I gave you some numbers about population growth. These numbers are not the most recent, but this is difficult data to get. But what you're looking at here is metal production trends. This is not polymers, this is not ceramics, just metals. On the axis, you have different dimensions because diamonds and steel are produced indifferently. But what you're looking at is, over the years, how the production of metals has grown in our society, and that exponential growth that you're seeing is continuing on. So we're using more and more stuff. That's the takeaway. Now, where's all this stuff coming from? It doesn't come from Home Depot. It comes from the Earth, planet Earth, where we take the ores out of the Earth and we have to extract them out. And ores have grades. If the ore grade is really high, that means you don't have to take so much stuff out of the Earth because it's rich. If the ore grade is low, you got to take more stuff out. Look what's happening with the trends in the ore grade. That's going down. So all of you are here, technical people. So when you have two things going in two different directions, it's not a good thing. It's a wreck that's going to happen. A couple of more examples. Computer chips are wonderful laptops that we love so much. Look at what has happened in a period of, 1980, 11 elements in the chip. Today, it's 52. I was in Paulina's office, and right above her desk is this periodic table. She was looking at me, I was looking at that thing, and realizing that we're using most of the periodic table. Okay? Now, you look at the recycling rates, end-of-life recycling rates of these elements. You don't see too many things that are in the green there. And I think all of you in this audience know what the lanthanides are. The recycling rate is less than 1%. Now, you might say that's a UNEP 2010 slide, where's the 2020? Actually, that's a mistake. I didn't put the 2020, but it looks very similar. There's not much change. So recycling rates are ridiculously low. And if you look at the world, the planet Earth, Australia is actually at 54% recycling rate of all goods. This is not just metals now, polymers, everything. We're about 37%. This is most recent from USGS. And if you look at Latin America, you look at Africa, you look at Asia, it's pretty much not there yet. In the US, the recycling rates in the US, for a variety of things, at the very, very far right is PET bottles, not a big number. Huh? Beverage cans, where I have the green thing there, is about almost 50%, meaning 50% of the beverage cans are not ending up to be recycled, ending up in landfills or whatever. Anomaly is lead-acid batteries. I'm going to come back to that a little bit later because it has a lot to do with policy and the business model, okay? Now, don't you wish that everything was like that, right? I'll come back to that. Again, I'm trying to set up some context here, so just for you to be aware of how important criticality is, materials criticality is. Now, we look at properties like fracture toughness, we look at properties like damping characteristics. Where's Julian back there? Strength, ductility. But material criticality is a property. If you cannot have it, it's not available, it becomes critical. And unfortunately, this doesn't have to do with atomic bonding or other things. It has to do with geopolitical forces, okay? Let's look at the continent of Africa. The continent of Africa is so rich in minerals. Platinum, which is used for a lot of things like catalysts and all kinds of electrolyzers, etc. 85% of it is coming from Africa. Chromium, cobalt, right? These are really, really important elements. There's no wonder that a lot of the foreign policy of certain countries are directed to Africa, where I know that China has all kinds of scholarship programs in Africa, all kinds of things of that sort. I'm sure because they love Africans, but I think there's a more reason than that, because there are a lot of minerals in Africa. For those of you who haven't seen ores and things, I don't know how many of you had any introduction to extractive metallurgy, but those are a bunch of ores that you see on the top left corner. Some of the mines and huge equipment that's utilized to do the mining. There's a fellow there standing next to a tire. That's it's not a midget, it's a regular guy. So we're talking about big, big equipment here. If you look at the various continents, China on the far right, all of the minerals that they have available, mineral materials that they have available. Africa, but not so much on the North and South America. More importantly, rare earth elements, critical, which so many applications. Much of it is coming from India. I think it's 90, I cannot see it from here, it's too small. It's 91% from China, okay? Now, why am I focusing on rare earth elements? We need them for so many applications. Magnets, neodymium for high performance magnets, traction motors, wind turbine generators, terbium and europium for LED, OLED displays, et cetera. And we don't have them here. Just a couple of days ago, USGS produced a list. I know it's an eye chart, but that's a big list of all of these things that are critical. Take any one of them, I don't know, tungsten, indium used in flat panel displays. These are all critical, meaning, we have a shortage of it. I chose not to put it in this lecture because of the limitations of time. But if you look at commodity prices and you look at prices of these elements, McKinsey has a recent study, it's increasing annual compounded growth rate about 8.5%. So in the last 10 years, the prices have gone up by 200%. Not sustainable. Now I'm going to plant a few seeds, I'm going to come back to it later, about policy. Something that is not known very well, if you look at the rare earth production over a period of time, going back to 1900s, US actually dominated it. There's a mine called Mountain Pass in California that produced rare earth metals. I'll give you a hint, this is before EPA. However, the way they were producing it was actually not very environmentally friendly. There's a lot of toxic waste that was going into the earth. And EPA said, you can't really do it this way. And to do it right, to do it properly, was not sustainable. The business model didn't work. So they essentially went out. At the same time, China was opening up its doors. And they really were not a big industrial power. And, I think the slide speaks for itself. Now, Mountain Pass just recently started a new company where the government actually has 45% of the equity in the company, which is an interesting, another chapter and conversation for another day. So I think I've set some context as to how important materials are for all the things that we want to make and do to enhance the quality of life on this planet. Now, material circularity, I'm not sure how much time you spend on this in your courses, but for those of you who are not in material science, what we do really is understand the processing of materials to influence the structure that evolves and how that transforms into properties and performance and, go from the science to engineering, that scale, the tetrahedron, if you will. And there's all kinds of interactions between them. And essentially, it's a process by which we develop new materials and properties. We select materials for specific applications, and we optimize the performance for a given material. That's really the material design process. All of you know this. You practice it. What's missing in this diagram? I mean, we talk about material science, processing, structure, synthesis, structure, properties, performance. What's missing is how do we recover and reuse it? We don't really spend too much time on it, right? We focus so much more. If you look at the circularity map, this is Alan Lew and I came up with this about a year ago. The focus is usually here, right? We start here, that's where all the ores come from. There's mining, raw materials, and we finally make the product, people use it, and end of life. But most of our focus has been on this part here. How to make it, design new materials, discover new materials, new properties, whatever. But, we really need to focus on this side too, which is a huge opportunity. It's not just recycle, it's reuse, replace, reduce, remanufacture, recover, reuse, all the R's, right? So, huge opportunity. So the circularity thing, turns out, has been around a long time. Not only in literature, in philosophy, but in religion. So I'll digress from technology for a second. I was in Armenia for the first time about 15, 20 years ago. And Armenia is the country that decided to adopt Christianity as the religion of the nation in 305 AD, the very first country in the planet. So when you go to Armenia, you'll see a lot of monasteries, a lot of incredible old monasteries. This is one of them that I was visiting, and the monk was giving us a tour. And I kept seeing these things you see on the right here, the Rosetta Stone, But I didn't see one, I didn't see two, they were all over. So I asked the monk, I said, what's the symbolic meaning of this? He actually made me feel pretty bad. He said, you should know. The worst thing you can do when somebody asks a question. I said, I don't know. He says, well, in our religion, when you die, we want you to be buried, not cremated, because we believe that we're born to the earth and we go back to the earth. It hit me that circularity has been around a long time. It's not just a technical thing. So and many, many religions are that way as well. Now, let's look at the industrial system. Again, I'm talking about circularity here. It's open loop. There's a lot of waste. There's not too many subsystems. We use most of the periodic table. But the natural ecosystem, which has been around a long time, nature has been around a long time, it's all the opposites. So we can learn a lot from it, from nature, and see how we can adopt. And the weird part is that in nature, equilibrium is an indicator of well-being. In the industrial system, can you imagine Raytheon Corporation annual report saying, well, we haven't grown, we're so proud we've been the same for the last 20 years. It just doesn't work, right? It's not our system. However, we can learn a lot from it. We can learn a lot about what are the things that nature does that works. And one of them is this idea of cradle-to-cradle approach. One of the things I haven't talked about is carbon emissions, and something that many of you know about already, but this is a couple of years data, 59 gigatons equivalent of CO2 production. 12 gigatons of that is from industrial processes, and three materials, steel, aluminum, and cement production make up almost 50% of that. This is production. We're producing cement, we're producing steel, we're producing aluminum, and 50% of the industrial CO2 is from those three alone. Huge. So I think we need to think about it in terms of not only recovery, reuse, and recycle, but also decarbonization. Actually, just to let you know that we're actually starting an institute at UCI looking at not only rare earth metals, but also ammonia, which is so important for agriculture, and cement, and critical and near critical, like lithium and other materials like that. Yetman Chang is here in the room. He's been one of the pioneers in this whole cement domain with Sublime and some of the work he's been doing. Okay, so I think I've set the context here and what circularity is all about. So let's talk about some of the pathways to sustainability. There are really three different pathways. One is post-consumer waste, things that we use on a day-to-day basis that are waste. How can we take the waste and recover it and reuse it? Essentially create value out of waste, okay? The other one is production waste. So when we're making, let's say, aluminum from the ore bauxite, there's a lot of waste, like red mud. How can we utilize that waste or tailings from mines, et cetera, things that exist? How can we take that, recover, and bring value out of it and reuse it? And the other area is completely new, novel production technologies like, the cement production that you're doing at Sublime and other electrochemical or electrochemistry technologies. So that's the way we like to think about sustainability. There may be others, but I don't think so. I think those are the main areas. And I want to make sure that I mention that these are the technical aspects of it. So sustainability has not only technology, but also policy and also education. We'll talk about that a little bit later. So I'm going to take each one of these and just give you one or two examples in each, to give you the big picture. So when it comes to post-consumer waste, there's a lot of it, unfortunately. And for some of you who are in your 20s, you probably don't know what it was like 40 years ago, or maybe 50 years ago, but I do. But things were a lot different. We didn't throw things away that easily. We didn't waste anything in the kitchen. Everything was used. I'm a vegetarian, but I know what sausage is. Nothing was wasted, right? They used everything. And people repaired things. So I'm getting off tangent, which I don't want to do, but I think just one exercise. I'm not going to embarrass anyone here. How many of you have been to a cobbler in the last year or two? Okay, that tells you a picture. So in the old days, I still do it, when the shoe wears out, you get it repaired and you use it, you don't throw it away. All right, I told you that I've been very influenced by my time here about art. And this is a very famous painting by Georges Seurat, Sunday on the Grand Jet. It's in the Chicago Art Museum. And during the Impressionistic age, he sort of was a pioneer in doing it a little bit differently than the rest of his colleagues. And you're probably wondering, where is he going with this on post-consumer waste? Well, the reason I'm showing this is because there's a a photographer who was inspired by this and redid this painting in a different way. And this I'm borrowing from Brandy Chain, where he took beverage cans, consumed beverage cans, and redid the painting that way. All right, so you see the picture, right? I mean, from here, it's all beverage cans. And the reason I'm pointing this out is because today, and this is most recent data, we're using about 100,000 beverage cans. Every minute, 200,000 beverage cans, right? Whether it's soda, whatever, people drink, Now, the recycling rate is less than 50%, which just doesn't make any sense at all. So in North America, we have now an abundance of aluminum scrap. There are some cars like the F-150, it's all aluminum. They're coming to the end of life. I have a picture of what happens to these things at the end of life. But if you look at the numbers, about 1.2 billion kilograms of aluminum scrap in 2021, and that number is actually increasing. From appliances, cars, you name it, And previously, there was a limitation of secondary aluminum. It's called secondary, which is scrap that's remelted and reused because there were some sensitivities to chemistry, contamination. There are 300 different alloys of aluminum, so the scrap is a mixed bag, right? So it's been mostly downcycled, not upcycled. You look at the growth of just a commodity product, I'm not talking about vanadium or neodymium, I'm talking about aluminum, which is an abundant material. The growth is really, really high. So if you look at the numbers, in an average car today, about 500 to 600 pounds of it is aluminum. 20, 30 years ago, it was mostly steel, right? So it's a growth area, and we're going to have a lot more scrap. We're going to have a lot of aluminum scrap available, meaning we don't have to take bauxite out of the earth and go through all of the extractive metallurgical processes that consume a lot of energy. Recycled aluminum reduces the energy requirement by 95%. The amount of energy I need to make aluminum out of bauxite is, say, X. The amount of energy I need to recycle aluminum is 0.05x, 95% reduction. So at the end of life, what happens to these cars? Well, it's something like this. At the end of life, there's a whole bunch of companies, they dismantle it. They take all the good stuff that they can sell, like maybe a wheel or, I don't know, upholstery, whatever. And then it goes to a shredder. And the shredder is like it's like a huge Cuisinart, food processor. It gets shredded. And then it goes through a magnetic separation into what? Ferrous and non-ferrous. Through eddy current separation. How many of you have been to one of these? Have you ever seen one? Huge, right? Impressive as hell. And you wonder, oh, that's a car that's being shredded. And then that gets further processed into, I didn't make up these names, they came during World War II by somebody who was into telegraphic coding, into Zurich and Zorba. Zurich is mostly stainless steels, not much aluminum in there, whereas Zorba is mostly aluminum, but has also copper, some plastics and other things in it. The Zorba gets further processed through separation technology, mostly hydraulic with water, and or it gets exported. I was going to talk about that. It gets exported usually, but in the last 10 years, where was it being exported to? China and India, but they have their own scrap now. They don't need it. They're producing their own scrap, so they don't want it anymore. So exportation is really not an option. So it gets processed further to Twitch. Twitch is 98%. Again, I didn't make up these names. 98% aluminum. But remember I said there are 354 different alloys of aluminum, cast alloys, wrought alloys. It's a mixture. It's a real blend. So now the opportunity is to take the Twitch forget about bauxite reduction, extractive metallurgy, and to reutilize that. What has been happening in the last 5-6 years has been downcycling, where they make the lowest value aluminum alloy, like 380 for die casting. The opportunity is to make 70-75, to make 60-61 aerospace materials from Twitch. So that's the aim, that's the motivation, creating value out of waste, okay? Think about that, that's one takeaway, create value out of waste. So upcycling, not downcycling. So working with the fellow whose picture I had at the very beginning, Dave Spencer, and some other ATP, NIST big contracts, we've developed a sortation technology whereby the scrap sits on a conveyor belt, goes through. You can use XRT, you can use LIBS, you can use XRF, but essentially you're sorting it, and you have these bins of families of alloys. Not 354 bins, but about 6 or 7 different bins, you know, copper, magnesium, whatever. And then you do essentially blending, you know, just like they do, you know, they make scotch in Scotland, you know, they blend it, right, to get the right property, the right taste, in this case, the right properties. I should go back for a second and tell you that one of the challenges is how do you lay the scrap on the conveyor belt? Because there's a certain amount of time for the sensor to detect what it is and to tell it downstream which bin to go into. So if the scrap is too close to each other, it gets confused and you get a lot of errors. So one of the biggest challenges is how do you put the scrap on the conveyor belt? It doesn't sound very profound, but it was a really interesting problem. So that's what we're doing. You know, we're blending it. And through AI and machine learning, we have all kinds of algorithms now where actually you make 70-75, 60-61, upcycling from Twitch. So Twitch becomes like a gold mine, you know? And but we walk the talk. There's a company that my students and I started called Solvus Global, which has very much influenced by the flagship pioneering model. It's more of a studio model, where we have these companies that have spun out, and one of them is this company Vallis, which actually does this technology for, you know, as a startup. The students, I want to give credit to them. One is I do this really to show, especially the students here who are in MSc, that yeah, you can go work for a company, but you can also start your own company. You know, there are opportunities. You can go to academia, you can go to a national lab, you can work for a small company, for a large company, but there's also opportunities that you start your own company. So Aaron Bird is the CEO, and Sean Kelly, they look a little bit older than those pictures there, but you know, time goes by. That was about 6 years ago. So we actually have a company called Vallis that actually does this to optimize product sortation and quality monitoring. And I'm very proud to tell you that Emily Molstad, who was also a student, is now the CEO and co-founder of this. So just an example. Now, I told you about all the problems of putting scrap on a conveyor belt and sortation and all that. In steel making today, we don't really use open hearth furnaces. We take steel scrap, we melt it in electric arc furnace, we check the composition, you know, we taste the soup, see how it tastes, and then accordingly we add a little salt or a little salt pepper. Not really, we add moly or vanadium, whatever, but essentially we tweak it to get the right composition, and then we cast the steel, right? That's how steel is made today, through a lot of scrap. In aluminum, doing this sortation is expensive, difficult, even though it goes against the grain of the company Vallis, but always be in charge of your own obsolescence. That's one message I can give you. Obsolescence is going to occur. Make sure you're in charge of it. Don't let it happen to you. You be in charge of it. So what we're doing now at UCI has been very successful. We're taking the Twitch and really studying its DNA. Temporally, with time, it changes because, you know, how people get rid of their cars, and geographically. West Coast, Midwest, Atlanta region, Northeast, over a period of year, every month, about 100 pounds. It's labor intensive, but we analyzed the twitch DNA and figured out a way to do what we're doing in steel where we don't sort it, we just melt it and then figure out how to make the soup taste good, metaphorically speaking. So it turns out that, this is too farly animated, that if you look at the composition of twitch, that there are certain phases that come out early on, the intermetallics, and then there are certain phases that come out later on. And what we figured out that if we take it and fractionally solidify melted twitch, fractionally solidify to about 0.65 fractions solid, there are two regions there, all right, and separate them, that we have actually value in both of those components. Region 2, which is very rich with the other elements, can actually be used as like a master alloy for making some of these alloys. And the region 1 can actually be used as a structural material with very, very high integrity. In fact, it has some amazing properties, And we really do it by, I'm not going through all the details of the process, it's being all patent and all that, but the concept is really came from a filter coffee, How do you separate a solid from a liquid, I think you get the idea, right? So this is one of the exciting areas where we're looking at taking the scrap aluminum, not sorting it, just melting it, and then apply liquid metallurgical technologies to separate it. Another area for production, post-consumer waste is lithium-ion batteries. So even though may not be as popular today, EVs, with this administration, I'm telling you that all of the companies are investing in it, whether it's in Europe or not. So EVs are here to stay. Lithium-ion batteries are here to stay. And many of the batteries are actually not made here. If you look at that chart, a lot of them are in Asia. But we're focusing not on the making of the battery, but how do you recover and reuse? I don't have time to go into the details. There's an anode, there's a cathode. The cathode has a lot of precious elements in it. You all know about it, right? There's cobalt, there's nickel, there's lithium. So how do you recover and use it? So one of Yet Min Chang's postdocs, Yan Wang, we hired him at WPI when I was there. He looks a little bit younger there, right? And Eric Gratz, who was a postdoc of mine. So we figured out a way to do this where we can recycle lithium-ion batteries. And, well, it's not a story for another day, but so Eric wanted to be the president. I said, okay, go ahead. You got nothing to lose right now, and this is a good time for you to do it because if it doesn't work, it's going to be fine. And we actually developed a process, which is now a real company, Ascent Elements. It's a $1 billion company, where it's a hydro to cathode technique where we take the batteries, we shred them, and we put them through a press. Essentially, we create the black mass, which is so valuable, that has all the cobalt, nickel, and lithium, and you can make all these batteries out of the black mass. And if you compare this to the traditional pyrometallurgy approach that Umicore has been using for years, or traditional hydrometallurgy, the hydro to cathode is a much more efficient and more robust way of doing it. So this company is now in existence for about 8-9 years. You can see the shredding operation on your left, and the black mass that's coming out on the right. So it is a very good example of how you can take production waste, recover and reuse it. And just to tell you a little bit about the company, it's now, another day we can talk about startup companies, whether when it gets diluted or when you have complete control and there's no outside money coming in, or you have neither one of those, you just license the technology. But this is one where it's completely diluted. You can see the number of dollars that came in. And now it's as I said, it's a major corporation. And a new plant's being built in Kentucky, as you can see there. Let me move on because I think time is going by too quickly. And I'm going to go through a little bit more. I'm not going to go through everything because it's more important that we have some time for a Q&A. So production waste is another one. Red mud. Every pound of aluminum, 3 pounds of red mud. A lot of scandium is in it. So there's a whole opportunity there to take the red mud, which is a production waste, and recover the scandium. In the rare earth area, extraction by chelators, separation, metallization, purification. In this slide, what I want to focus on is just on the extraction. There are a lot of mines, especially in Montana. We were just there recently. These mines are no longer operational, and there's a lot of tailings. There's a lot of waste, and it's a gold mine as to what you can do with it. So just some pictures of what these look like. You can see the abandoned pump turnoff on your right there. There's a lot of good stuff in there. And if you use the appropriate tweezer, if you will, chelators, you can actually extract the rare earths out of it. And a very quick flow chart from the tailings, you can see that you can actually get the rare earths out of it. We're actually working on this right now, and we're preparing for a congressional plus-up for it. In the novel production technologies, one of your new faculty members, Xiaolu Wei, is a really good friend and one of Chem Tassan's PhD students. What he's been doing in Germany, in Dirk Reiber's group, is shortcutting this classical multi-step alloy making by just going to the ingredients at the beginning and processing it, whereby alleviating all the middle steps. And he did this recently, and it was a Nature article. I'm just going to give you a couple of snapshots of it. We're looking at INVAR, which is iron nickel. I'm not sure how many of you remember this, but this guy, Guillaume, got the Nobel Prize for INVAR back in 1929 or 20, I can't see it, 1920. I wasn't around then, so I don't remember, so excuse me, 1920. But, you know, INVAR is about what? Iron and nickel, 30% nickel, but nickel is a much more, it does a lot more damage when you extract nickel out compared to iron. So their approach very quickly is that they start with the iron and nickel powder and essentially make INVAR directly through a process, shortcutting the whole thing. So I'm not giving enough justice to the work. It's an amazing piece of work. And he'll be here with you soon, and he'll be doing a lot more stuff like this. But essentially, the idea is that, you know, you're shortcutting it, and so what? So what is that you are decreasing the energy consumption, and you're eliminating a lot of steps. Just one more, very quickly, on the hydrogen. We have a very, very large hydrogen initiative in the University of California, Irvine, where there's a lot of work going on electrolyzers, but the whole scale, you know, from electrocatalysts all the way to plant scale stacks. And much of this is being used now to replace bulk chemistry and thermochemistry, a variety of applications, including cement. So it's really, really very exciting. I want to finish off by the 3 axes that I want to make sure that we pay attention to. So far, what we have talked about is the bottom one, innovation, the science, the technology. Policy is really, really important. Policy, because, you know, human beings are Pavlovian. Our behavior is dictated by policy. So, for example, components, we talked about production waste. If the manufacturer is responsible for the end of life versus the consumer. Right now in America, when you buy a car, it's yours. At the end of life, it's your problem. Either you trade it in, you gotta sell to a friend, you gotta get rid of it. What would happen if the policy now, the rule of the land, is that you make it, you gotta take it back, and you gotta figure out how to dismantle it. I gotta tell you, when that happens, things are gonna be designed very differently. There'll be able to at least disassemble it easily, okay? Because a lot of things are manufactured where you cannot disassemble it today, unfortunately. So role of policy is really, really important. So when you saw this, you said, wow, that's great. Lead-acid batteries are all yeah, there's a business model. You take it to the dealer, they take it back, they pay you money, you're done. Then they sell it to somebody else. What happens to it? What happens to it? I want to come back to it. There was an article in New York Times yesterday just about this, if you read it. You're probably wondering, why am I putting this up? This is Southern California, not too far from where I live. Beautiful road, right? Pretty, clean. You're driving, and all of a sudden you see people in front of you throwing things out of their car. They're littering. You say to yourself, what is wrong with those people? What on earth are they doing? Are they stupid? Are they crazy? What's happening? They're cleaning their car. Their car is clean. Unfortunately, guys, that's what we do with a lot of this stuff. This was yesterday's article. A lot of these lead-acid batteries end up in places, South America, a lot of electronic waste particularly. South America, Africa, this is Nigeria. And the way they process it, obviously there's no EPA. If you just look at the numbers from yesterday, it's crazy, the lead poisoning that these people are going through. So we need to, policy is important. All of us are engineers, but we need to be advocates. We don't have enough congresswomen and congressmen in Congress who are engineers. We need to be advocates. So we're living in a global community. It's not what's good for America, it's what's good for Germany. We got to think about what's good for the world, okay? It's a global community. So I'm going to finish by thanking you by giving you a couple of takeaway messages, which really is a repeat of, reduce production waste, reduce post-consumer waste, design and manufacture disassembly, create value from waste, and implement circular economy, recover and reuse, and create value. And then try to make things that can be fixed, repaired, disassembled. And I'm going to thank you for your attention. And I really want to have some time for a Q&A, and I hope we can. Thank you.
Thank you so much, Dr. Apelian, for this scintillating presentation. Let's take questions, and we would like to allow our students the first chance to ask questions. So please don't be shy.
Yeah, there's no stupid questions.
Please.
There may be stupid answers, so don't worry about it. Did I
pass the
convert
mic.
you guys to join material science and engineering? Yeah? Good. Yes, sir.
Thank you. Thank you for the talk. So my question is, like, in the era of AI, what do you think are the potential opportunities for AI to accelerate material or to propel material sustainability? Thank you.
Wonderful question. Did he pay you to ask that question? I don't need it. There are a couple of things about your question is a rich question, okay?
So what opportunities may AI offer to material sustainability?
AI is going to replace a lot of jobs. A lot of people are going to be out of jobs. It's not going to be people who create value. So accounting things, coding, things that AI can do. The kinds of things I'm talking about here, AI cannot do. So the way to think about, even though your question was not exactly that, the way to think about it is that, what am I going to do? What am I need to learn, especially when I'm here at MIT or throughout my life, because education doesn't stop when you graduate, right? What am I going to do so that I make sure that whatever it is I'm doing, AI cannot do? Because AI is going to be able to do a lot of things. But AI is not going to be able to figure out innovation. It's not going to be able to figure out a lot of technological, scientific things, right? You know, physical laws and how to apply those to certain things. AI is going on the data, right, that exists. Now, when it becomes more and more intelligent, that may be an issue, but it's not there yet. So I like to think about it this way. Work on the things that AI is not going to be able to do. AI is not going to be able to convene a meeting. AI is not going to be able to figure out what you're thinking as I'm looking at you, right? So in addition to, even though it wasn't your question, in addition to all of the incredible things you're learning here in science and engineering, technology, the human dimension is so critical. Work on it, develop it. How do you listen? How do you listen? Listening is when the person hasn't said what they are. Listening is not hearing. Listening is hearing what the person hasn't said. How do you listen? How do you communicate? How do you tell your story? How do you care? You know, those are the things that are going to make the difference. But actually, in the things that I'm talking about, processing, obviously I'm biased, manufacturing, making things, products that people need, you're going to do okay. AI cannot do that. You know, I was saying some of the students at lunch today, the guy who's got a pizza shop, makes good pizza, is not going to be threatened by AI. Why? He's making something that AI cannot make. So when you create value by making something that somebody wants and is willing to pay for it, you're golden. Yeah. Does that help?
Yeah.
But the thing I worry about is that when AI gets to be so intelligent, probably 20 years from now, and robots get to be so intelligent, and these guys get together and say, you know, these human beings are stupid, let's get rid of them. That's what I worry about.
Do we have Professor Tazan? Oh, let's go with Carlos first.
As you said, science, engineering, and economy is like.
Yeah, so people can hear you.
So as you said, science, engineering, and economy is like very highly intertwined. How's maybe your response to certain like leaders in sectors where their business model may not highly support or like be highly wasteful and are like kind of against change, especially as well as like governments how you may try and convince them to go on a more circularity path?
That's a tough question because it has to do a lot with what motivates people. And it doesn't sound very profound, but we know from history, we know from examples, we know from experience that doing the right thing always pays off. Always pays off. So if you're doing things for the wrong reasons, you may benefit maybe temporarily. I'm talking about corporations now, right? So you look at Patagonia, for example. Amazing company. In what way? They actually tell you, don't buy a new one. We can repair it for you. They actually have a whole program. And what they've done by that is that they've gotten tremendous loyalty, customer loyalty. They're more expensive, but people go there because of that. So they cater to a special market where people care about nature, care about these things, and they're doing it right. So you can't tell people what to do, but corporations that are doing the right thing are winning. So taking consideration what I said earlier, be in charge of your own obsolescence. So corporations who make a mistake. Tylenol, 20 years ago, there was a big thing about Tylenol. They came out an hour later and said, we're going to pull it out. We take responsibility. We own it. Everything was fine. Look at Volkswagen 4 or 5 years ago, where it took a long time and $50 billion penalty that they paid for. So doing the right things always pays off. And hopefully people are going to learn that lesson. Yeah. Hope I answered your question.
Thank you so much. We are at the end of our hour, so before we wrap up our Wulff lecture, there's two things I want to do. First of all, I would like to thank Dr. Apelian to bring up the ideas of circularity and innovation and how being good for the environment can also be good for the bottom line. And if you are interested in innovation, I would like to tell you all a little factoid about material science and engineering, is that we actually by number happen to be the most innovative department at MIT. Our faculty is 2.8 MIT faculty. We are 31 people, but we are responsible for 9% of MIT's total patent output per year. We happen to... So, per capita, our faculty and students are the most innovative faculty and students in the most innovative institution on the planet. So if you're interested in creating solutions for environment, sustainability, you should be majoring in material science and engineering, because you're also going to be doing good while doing well. So, with this, as an example, Dr. Apelian is a really shining example of doing wonderful things for our sustainability. And in our appreciation for Wulff lecture, we would like to present him with this unique MIT gift, which is our glass beaver made in our glass lab.
Oh, this is wonderful.
So MIT has a beautiful glass lab. And you cannot get this beaver unless you present a Wulff lecture, right, Professor Chang? This is only the most celebrated material scientists on the planet get to hold the glass beaver.
Thank you.
Thank you so much, Dr. Apelian. Let's thank him.
It's been a real pleasure. I hope you got something out of this lecture. It's been good to see you all. Thank you for coming, and wish you all the very, very best.